working for a change. We're going to be starting chapter 10. I think I should talk a little bit about your test. Chapter 10 is going to be déjà vu because a lot of it is the same stuff that we've been doing. They just add a little bit more detail. They add a few extra terms and maybe focus on some terms that we just glossed over. And we're going to be looking at essentially estimating a sample proportion, either a single or a difference, or a population's mean, either a single or a difference. And it's going to be full of confidence intervals. So a lot of the same regurgitate. In a way, I'm kind of glad because not a lot of you were as comfortable with it as I thought we were. So maybe I wasn't beating the dead donkey enough to kind of make sure that we could do it. So that's kind of what we're going to be doing over the next few weeks. We're going to be delving into in a little bit more detail how we estimate a proportion or a mean. And we're going to use various kinds of confidence intervals. And that is pretty much the gist of it. So I'm looking for my right pen. Let's get started. Good place to begin is population again. And I'm trying to estimate the population proportion. P. And I do that by collecting a sample, which we'll call P hat. And that sample will have a size N. And what we're trying to create here is an interval of values that hopefully will contain that fella. And we tend to do that by using what's called confidence intervals. And a confidence interval for a single proportion at least is P hat plus or minus a magic z-score times the standard error, P hat. And the magic z-score can take all sorts of values. And the types of values that you're going to be seeing are ones that you've seen and a few extra. So you could be looking at a 90, a 95, we've seen them, a 98, and a 99. And depending on what kind of confidence interval you have, there is a magic z-score that belongs with it. Now these guys, these magic z-scores, can be found by using the t-distribution table with an infinite degrees of freedom, which I'm going to show you where they're hiding. Because one of the questions I noticed that wasn't done so well was you weren't using the right magic z-score. So hopefully you're looking at the t-distribution table. This guy here. Now, if you scroll down to the bottom here, you see the guy that says infinite? Here he is here. These numbers here correspond to these confidence intervals. So 90, for instance, is the second one. So 90, that's this guy, is 1.645. 95 is 1.96. 98, which is this one, which is a new one, which is 2.326. And 99, I think it's this one, let's check it, 2.576.
I'm sorry, what did you say infinite was referring to?
Infinite is, if you're looking at the screen, I hopefully I'm doing, is this bottom row. Infinite is if you had an infinite sample size. For a t-distribution, anything that's really big is pretty much infinite. You can pretend it's infinite. What that does is that this table actually contains the magic z-scores. Just giving you this as a reference. The best thing in the world would be just to write these things down, right? Just to write those guys. If you did, then you could just have them on a card and they'd be there when you need them. So these are the magic z-scores that you need when you're trying to estimate a population proportion. And these are pretty fixed. So when you're doing any kind of proportion question, this number here, this magic z-score, is one of these numbers typically. Now, when you put together this piece and this piece, you get a guy that's called the margin of error. So for instance, you may get a margin of error of 0.02, which we would probably call 2%. So you would be talking about that whole thing being equal to this. So you might get a question where they've done all the work for you. They haven't even bothered to show you where it came from, but they might have said, we're estimating this value. And the answer that we got was 0.71 and a margin of error of 2%. Now that guy there would be the sample. And this fella here, the entire thing, is the margin of error. And you get that by multiplying this number here, or one of these numbers, by whatever the standard error is. Now in that world here, you would convert it into a confidence interval, which looks like that. Or you could use percentages, which I prefer. So in this particular question, we would be, let's say it's a 99% confidence interval that I've just found. We could say we are 99% confident that somewhere in that range of values, the true population proportion is. So you might be asking things like, are you in favor of lower taxes? And the answer is that the population, somewhere between 69 and 73, are in favor of that. Any questions so far? I mean, this is pretty much just regurgitating what we've got, maybe doing it a little bit more formally, but that's it. So the typical kind of question after we get to by the what's a sample, what's a proportion, and so on, is that you have a story where you collect data. So I'll do my classic start again. Let's suppose that you ask 200 people. Would you vote for someone if they paid you? Interesting question. Don't know why it came into my head, but never mind. It's in there. And out of this sample, 23 people out of 200 said, yep, if they paid me, I'd vote for them. And we want to see, using only this sample, what the population, the entire voting population would be like, and whether they could, we could shed some light on what kind of range of values the true answer is. Okay, well, right now we know as an estimate, as a single number, that it's about 11.5%. But what we don't know yet is it likely to be 11.5, or is there quite a big range, or is there quite a small range? How's that going to work itself out? Well, that's why we have different confidence intervals. So I'm going to pick 2. I'm going to pick a 90, and then I'm going to pick a 99% confidence interval, and we'll sort of compare what they look like. Well, before I even do the work in calculating these two guys, let's look at big picture thing. Can you imagine that this represents the start and the finish, right? So there's some kind of scale going on here. The start and the finish for a 90% confidence interval. Would you expect a 99% confidence interval to be an even bigger interval or a smaller interval? What would common sense tell you?
Smaller.
I didn't catch that.
Oh, smaller.
Oh.
But it's bigger.
Oh, it's bigger. Okay.
Yeah.
Sorry.
Well, I mean, could go one side there. Well, let's try and think of why it should be bigger, just logically, right? Doing calculations. Right. If everybody in here, you're 90% sure. If you wanted to be even more sure, don't you need to have all the 90 plus some extra to get that extra 9% to be sure? Right. So the interval, if it's large, right, you're more likely to have the right answer inside it.
Mr. Robertson,
Yes.
West is in the waiting room.
Oh, thank you. Okay, I'm going to have to close this window off and open up participants and let West in. Well, she may have been, but she's not. Oh, West is here. She's inside. Gone to this.
I just got the email about it.
Okay, so it might have been a delay in the ether. So if you can imagine, that is a 90. And this was a 99%. If I'm being silly here, but if I wanted to be 99.99% sure, can you imagine that the interval would basically be almost everybody? So we have a balance here. We want to have a kind of an interval where we think, because we're never going to be sure that the true answer is in, and we'd like it to be reasonably small, because small kind of gives us a good idea of where it is. Whereas if the answer's huge, right, if the interval is huge like that, we really don't know anything very useful. I mean, can you imagine I said the answer was somewhere between 1 and 99%? What does that tell me? It tells me almost nothing. Right? So there is going to be a balance between these things. So before we calculate it, I'm going to do a 90, as I said, and a 99. That should happen. So let's see. I think I'll do it in a separate one now. I have p hat, which is 0.115. Q hat, which I think everybody is good at, so don't need to do that one. N, in this case, is 200. We need to calculate a guy called the standard error. It's basically akin to the standard deviation of the sampling distribution. And it has a formula. And I'm not quite sure how this happened, but at least 2, if not 3 different people forgot the N. I don't know what happened there. Right, there's a P, a Q, and an N in it. So in this question, it's going to be a 0.115, 0.885, and it's going to be divided by 200. Square root of 0.115 times 0.885 divided by 200. And the answer I get is, to 3 decimal places, 0.023. And I also need to know what the magic Z-score for a 90%, because this is a 90% confidence interval. And I had that a minute ago, and here it is, 1.645. Now, when you do proportions, it's Z-scores. And these numbers don't change if the sample size is different. So if the sample was 2,000 or 20 or whatever, it'd still be these guys. So for proportions, Z-scores are fixed numbers, right? They don't change. It doesn't matter how big or small the sample is, as long as it's usable. It's same number. Right, I've got all the pieces. A 90% confidence interval is going to be p hat plus or minus the magic Z-score. In this case, it's that guy, and the standard error, p hat. And so it's 0.115, give or take a Z-score, which is this fella, times a standard error, which is this guy. And if I multiply 1.645 by 0.023, I get the answer 0.038 to 3 decimal places. Now what happened here was a little, I don't know what the reasons are. It's hard to sometimes think why people do what they do. But some of you just thought that's the answer. But it's a confidence interval, and really to be a real confidence interval, we need an interval. We need a start number and a finish number. And some of you just didn't do that. 0.115, take away 0.038. And so I get 0.077. And then 0.115, add 0.038, and I get 0.153. And that was totally acceptable. It would have been probably a little bit easier to understand if we did that. So what we can conclude right now is that we're 90% confident that the percentage of people who would vote for you if you gave them money to do so is somewhere between 7.8 and 15.3%. In this question, the one we've just finished doing, that guy there, which is basically 3.8%, is the margin of error. That's its name. So if this was a news story on CNN or whatever, they would say, I don't know what their headline would be, but they'd saying that you can buy votes. 11.5% of Americans say that they would vote for them if they were paid to, and the margin of error was 3.8%. And that would be the language and the words that would be used to describe a confidence interval. Now, the only difference in creating a 95% confidence interval, the only number in this entire formula that changes is the Z-score. So it's still going to be p hat. It's going to be a magic Z-score for 95. Everything else is the same. So it's going to be 0.115, give or take, the magic Z-score for a 95. I think it was a 95 I chose. Oops. Stick to my story. Let's do a 99. So the only number I need to change is the magic Z-score and the standard error, and all the other numbers stay put. So here we go, 2.576 times 0.023, and this time I got 0.059, which is what, 11.5%, give or take 5.9%. And let's see what that looks like. 11.5, take away 5.9. So it's 5.6%, 17.4%. Okay, let's try and visualize what that looks like. Imagine we got a little number line. And we'll start at 5, 6, 7, 8, 9. Try that again. 5, 6, 7. Very, very crude number line. 5.6 is about here. 17.4 is about here. All the numbers between here and here could be the population percentage. How many people in the entire population? And that's if you do a 99% confidence interval. 7.8 is about here. 15.3 is about here. And between here and here, that's what a 90% confidence interval. Do you see what I'm getting at about the size of the intervals is different for a 90 compared to a 99? That's a truism. That happens no matter what the story is, no matter what the p-hat is, doesn't matter. The only thing that really changes is the Z-score. And because of that, the margin of error changes. So if you do a 99% confidence interval, your margin of error is almost 6%. If you did a 90% confidence interval, to see how your margin of error is only 3.8%, right? Smaller margin of error, smaller interval. Bigger margin of error, bigger interval. Right. Continuing with this story that I've just made up, we should test right at the beginning. Can we do it? Should we do it? Well, there are a couple of things that you need to be aware of, and this is big picture stuff is. Do we have good data? What we typically mean by that is unbiased. Well, let's assume that I got a nice simple random sample. That would be a good start, right? So I would say check. Let's pretend that was true. I would still fail this entire analysis on my second piece of the puzzle. If you ask people, would you vote for someone if they paid you money? Is there a possibility in that question that a reasonable number of people could lie? And we call that, in this particular case, response bias. People don't want to be thought of as badly, so they might say, no, I'm a very honest person. I wouldn't vote for someone just because they paid me, right? Even though the truth might be, well, if they gave me a couple $100,000, I probably would, but I'm not going to tell you that, right? So I would fail it on that, but we have to be aware that that is a possibility. And then there is technical reasons. I think we touched on this at least once, but we may not have dealt with it in any great detail. You cannot conduct one of these tests, right? These hypotheses, but creating a confidence interval. You can't really do it if NP, unless this is true. Do you know what number NP hat and NQ hat must be bigger than or equal to?
Was it 10?
10.
It was the magic 10. And in this particular story, check and check, right? You agree? So, is the data good? Well, hopefully it's a random sample, but it might fail because of, well, you could ask the question, right, badly. Couldn't you ask it in such a way that you might bias the data? Or it could be response bias or all sorts of bias like that. Could fail under technical reasons. Now, the third one is how useful is the prediction, right? I've created a confidence interval, but how useful is it? Suppose I was asking that same question, but the interval ended up being 5% to 95%. Would you agree that that confidence interval is pretty useless? You might as well just guess, right? The answer's somewhere between 5 and 95%. When would that happen? That would happen if your data sample was really small. Suppose you only asked 30 people, right? Would they do it? With a very, very tiny sample, you get ridiculously big intervals, right? Mass start to finish. So bear in mind that that is important. And the last thing that we want to look at is how confident are you that you have the correct value in your interval. Now, this guy doesn't depend on sample size or anything else. It just depends on what confidence interval you use. And we have talked about this before. If I do a 90% confidence interval, isn't there a 10% chance that my interval doesn't have the right answer in it? Right, 10% chance of it being wrong, right? Confidence interval, here to here, 90% confidence interval, 10% chance it's wrong. On the other hand, if I do a 99% confidence interval, isn't there only a 1% chance that my answer is not in that interval somewhere, right? The real population value. Now, because most people have a kind of threshold of how wrong are they willing to be? How much risk are they willing in being wrong? Can you understand why 90%'s at the bottom end? Right. Now, could I do a 50% confidence interval? Actually, you could. Would you want to make an interval where half the time you're right and half the time you're wrong? Wouldn't it be easy just flipping a coin and saying yes? Because isn't that probably going to be just as likely to be 50% right as 50% wrong? So we stick to kind of standard ones. This textbook drives me crazy sometimes. I hate that interval. I do not like that confidence interval. Nobody in normal world of statistics would use that, but you're going to get homework questions where they have a 98% in it, so we'll do it. Against a 98 is a compromise between it ain't 95 and it ain't 99. I can't think of any other reason why you would need one like that, but they choose it. They don't have one, and I'm not going to worry about it either because they don't, but there is a 99.9% confidence interval that gets used occasionally, pretty rarely, but does get used occasionally. And that guy It's typically only used in extreme cases, like I would bet you things like I've said before, NASA probably uses, when they do data analysis, they probably use that one because they want to be like really, really, really sure that the interval they've got is within reason. So that's a kind of big summary of most of what I've said you've seen before. Maybe added a few other bits. And I'm not going to use the dead donkey analogy anymore because it didn't work the last time. So we'll use a different analogy. Would you bet your house on it that you understand this? Right. So if no, you're not there yet. Right. So if I'm moving along that kind of threshold, then let's do another one. Let's find homework. Oh, darn it, in space. Okay, what are you doing? Right. Zoom was being weird for a second, but it seems to have settled down again. Right. So first thing I'm going to do is we're going to look at homework 10A, which doesn't really get too caught up in the number crunching yet. Make it a bit bigger. Not how big I can make it before it goes wonky there. That's probably it. And we'll kind of do these guys together. They're pretty easy to do. In each part of these questions, explain whether the proportion that is described is a sample or a population proportion. So we ain't going to overthink this. In the 2010 US Census, it was found out that about 1 in 8 Americans were at least 65 years old. Okay, what's that 1 in 8 American? Is that a sample proportion or a population one?
Population.
And the key here was that word there. It's easy to overlook because you just think, oh yeah, they did a census. A census is more than a sample. Theoretically, at least, isn't a census you asked everybody. So it's a true answer for the entire population. So we put that one there. A randomly selected group of 500 registered voters in your state was asked who they intend to vote for, right? The classic one. And who knows how many? 42 said, I'm going to vote Royalist. Is this a sample proportion or a population proportion? This one I think is easy, isn't it? I see your mouth moving and I'm taking it, yes. In a clinical trial done to assess the effectiveness of a new medication for asthma, a satisfactory relief from symptoms was experienced by 50%, 57%, and it was a 70 participant sample. Well, I've actually answered the question, so it's a sample, right? Can you see a difference between a sample and let's rephrase that, a sample proportion and a population proportion, right? Almost all of them are going to be samples, right? Occasionally you see somebody asked everybody, in which case that would be a population.
I think it helps that it's a lot less wordy. I feel like last, the questions we did, it went on and on and on. And by the time
you forgot what the beginning was
right.
by the time you got to the end. Well, that helps, yeah. I mean, this is reflection and this is revision, and I understand that, but this in the chapter that's going to happen in 2 weeks from now, which is hypothesis testing, this is the bread and butter of what we want you to be good at, right? Because if you can collect your own data and you know what good data looks like, and you now know how to analyze it, you can actually get results that are useful to someone out of that. So we want you to be kind of good at it, I accept. This one is to talking about a population and have a story with it and words like parameter. So let's get the jargon again. A survey is done to estimate the proportion of adults who think that texting while walking across an intersection in a crosswalk should be illegal. Ooh, I'm just not sure. I mean, I understand that. I'm just getting distracted there. I think the world's full of too many laws. And if you start making laws as pernickety as that, it gets to the point where just life gets boring. I'm a great believer in the Darwin theory. Let dumb people do dumb things. They'll kill themselves off pretty quickly, and then the rest of us can get on with our life. So the Darwin theory is a good theory. If you're interested in it, you should look it up. So maybe we should just let them get run over by buses. That way they won't breed, and the next generation will be a little bit more intelligent. You know, I'm saying that with my tongue in cheek, right? Just in case you thought I was being serious. Okay, back to this guy. 56% of a group of 1,000 people said, yeah, good idea, make it illegal. What is the population of interest? There are 5 choices. What's the population of interest in this question? One of those is the
All US adults.
correct. Now that one might seem very similar, which it is, but isn't this group a small subset of everybody? Okay. You know what I'm like, so I'm going to get distracted again. I'm going to contradict myself now and say there should be a very severe law against cell phones and driving. I don't drive much because well, I do drive, but I don't drive much when my wife is in the car because she always drives because she knows I've only got one good eye, and for some reason that scares her. I don't think it scares me. I've been driving for ages and I've hardly killed many. Tongue in cheek again. Right. So anyway, I get to look out, and she's driven by people, and I saw once, this is true, cross my heart, there was a person with their cell phone on the side, texting with one hand, and I don't know how they'd done this, eating a sandwich with the other hand. So I don't know what was keeping the steering wheel from going somewhere. Now, I would have
People use
let
their
the
knees for stuff like that.
probably, yeah. God, I hope so. I hope it wasn't just luck. You know, it's a straight bit of road. I don't need to turn. Now, the only reason I wouldn't use the Darwin theory on those people is that they not only do they kill themselves, but there's a good chance they're going to kill someone else, right? So that one I would go. So back to this story, and I've distracted you, the cell phone ones. What population parameter is interested in here? Well, one of these 5 is the guy that we're trying to get the percentage for. A lot of reading here, so I'll try and find it myself so we can see it. And it's that one, I believe. Now, what's the sample? It's that one. And what's the value of the sample statistic? In this case, it was 56%, or as a decimal 0.56. Has anybody want to answer this question for me? Because I don't get to do what you get to do. See, in a situation like this where you could have the answer as a decimal or as a percentage, is WebAssign fussy? In which case it has to be one but not the other?
Usually it specifies.
Right,
Like
and in this
the
case,
box
since
will have a percent symbol next to it, or it will ask just for probability, which means decimal.
Okay, so if you don't see a percentage here, you're saying that they probably are looking for that?
I haven't tried doing otherwise yet, but I would believe so.
Okay.
Because a lot of the time they add their own units if it's something like that.
Right. So I'd just be on the lookout for that. But you have 5 guesses, right? So if it don't work one way, won't it? You just turn it to the other and you should be fine. Okay, this one is a very simple question. I just had to read it twice. The length of the box distracted me. Suppose you did a 99% confidence interval. The likelihood that the interval will not cover, is that 5%? Okay, I can't count. Is that 1%? And third time lucky, 1%. Glad they give me 5 shots. Do you see that little percentage that he was talking about? So it's kind of obvious now that I see that. So if I know I've got a 90% confidence interval, doesn't that mean there's a 10% chance I'm wrong? That's essentially what that is about. And that's pretty much all that is about. And that's pretty much the same kind of questions as before, so I don't think I need to dwell on that. Okay, this one here is getting towards creating a confidence interval. In this case, 41% of a randomly selected sample of that many adults said they do not get enough sleep, and the margin of error on a 95% confidence interval was 3.2%. So 41 take away that guy and 41 add that is what the interval is. So starting at this number, that's 40.8, I believe. And since they have the percentage there, that's good. And 44.2. So based on this 95% confidence interval, we believe somewhere between 41 and 44% of Americans don't get enough sleep. It's quite a high percentage. And then you write a little sentence with 95% confidence. We can say that the population of the, is it all adults or American adults? American adults is between 40.8% and 44.2%. Now, if you were doing something like this, the audience that you're doing it for kind of governs how you would phrase it. See, if you were talking to some other statistician or a scientist who's used to confidence intervals, wouldn't you probably tell them the confidence interval and all the other stuff that goes with it, right? The sample size, the confidence interval, and everything else. If you were just talking to your boss and your boss isn't interested in the other stuff, the boss just wants to know is, right, roughly what percentage do you think we're going to get next year, right? You would say somewhere between 40.8 and 44.2%. Isn't that all they want to know, right? Give me the bottom line. Tell me the interval. Somewhere in that region, I can live with that. But if you start telling people confidence intervals and other stuff like that, I think what's that phrase? Sometimes too much information is just as bad as too little. So think about your audience if you're ever doing this. And we have, I'm going to get a quick chat. I am now going to say perfect time and say hi, everybody, and bye-bye.